Imagine traveling faster than a bullet. You never leave the ground, and you never hit turbulence. You only experience pure, uninterrupted speed. What you are visualizing is the reality of the fastest trains ever built on Earth. These are highly specialized machines engineered to exceed 600 kilometers per hour. Right now, the absolute peak of this technology is Japan's SC Maglev. During testing, this specific vehicle reached a staggering top speed of 603 kilometers per hour. That is faster than many commercial airplanes travel during their takeoff roll. Reaching these speeds requires a departure from the wheel-on-rail design that has defined ground transit for nearly 2 centuries. Traditional trains depend entirely on one mechanical component, wheels, and wheels require physical contact with a track to move. That constant physical contact creates friction. At lower speeds, friction is manageable, but as you accelerate, friction becomes a violent physical wall. It generates intense heat, aggressively resists forward momentum, and causes structural damage that makes extreme speeds physically impossible. To shatter the speed limits of Earth, engineers realized they had to eliminate the source of the friction. They had to kill the wheel and remove physical contact entirely. To reach these speeds, engineers shifted from mechanical wheels to a system powered entirely by magnetic force. The replacement for the wheel is Maglev, short for magnetic levitation. If you've pressed identical magnetic poles together and felt them physically push apart, you understand levitation. Maglev systems use massive electromagnets to replicate that exact effect, pushing against the track to force the multi-ton vehicle to float slightly in the air. The exact moment the vehicle lifts off the guideway, all physical contact completely ceases. The mechanical friction drops to zero. While air resistance remains a factor, the magnetic cushion removes rolling friction, the main source of mechanical heat and vibration in standard rail. This introduces an immediate logical problem. If the train is hovering in the air without wheels or a combustion engine, how does it move forward? The answer is a piece of technology known as a linear motor. Picture a standard electric motor spinning to generate movement. Now imagine breaking it open and stretching it into a flat line for miles. Embedded electromagnets fire in sequence, creating a moving magnetic field that continuously pushes and pulls the train forward. Because there are no mechanical gears shifting, there are no jerks. There is absolutely no loud engine noise. Instead, you only experience a silent, perfectly smooth, and extreme acceleration. The guideway itself generates the electromagnetic waves that propel the train, acting as the primary power source for the vehicle's movement. Riding inside a maglev feels completely different from a normal train commute. Without wheels grinding against steel, passengers often describe the sensation as gliding directly through the air. But if this technology offers absolute physical superiority, why isn't it deployed in every major city? The reality comes down to massive financial cost and a complete lack of compatibility with the past. A maglev train cannot run on an old railway track. These systems require heavily fortified, deeply specialized concrete guideways packed with rare electromagnets. Every single mile of infrastructure must be built entirely from scratch. True technological leaps rarely bolt cleanly onto old systems. They require an entirely new world to be built underneath them. Despite the enormous price tag, nations like Japan and China are pouring capital into commercial maglev systems. They are doing this because operating at over 400 kilometers per hour shrinks what used to be a multi-hour commute between major economic hubs down to a matter of minutes. It is a vision of transit entirely free from highway traffic, free from weather delays, and free from the mechanical breakdowns of complex internal combustion engines. This technology changes the logistics of regional travel, making it possible to cross hundreds of kilometers in the time it takes for a typical city commute. The fastest train in the world proves that as we push the limits of speed, the ultimate future of ground transportation won't even touch the ground.